Curious, if you take a brick from a building or a grain of sand from an anthill and break it in half and then in half again, what happens when you can no longer divide it? For centuries, the debate was split between two possibilities. Either matter was continuous, like a block of wood that stays smooth no matter how small you cut it, or it was made of distinct particles, like individual grains of sand. Without the tools to see past the limits of human sight, there was no way to prove which side was right. In the 18th century, chemists began using weight to solve the problem. Antoine Lavoisier designed an experiment where he isolated reactive chemicals inside a sealed conical flask and weighed the entire setup. When the chemicals mixed and reacted, the total mass of the system did not change. This law of conservation of mass proved that while substances could transform, the total amount of matter remained constant. Other experiments showed that compounds were equally rigid. Water always consists of exactly 1 part hydrogen to 8 parts oxygen by mass, regardless of its source or how it was formed. These strict ratios suggested that matter was not a random mixture. If the mathematical ratios were this precise, the underlying components had to be uniform, repeating building blocks. John Dalton hypothesized that these mathematical rules were driven by particles he called atoms. He represented different elements with specific symbols, seen in these diagrams for hydrogen and oxygen. Dalton visualized how they combined to form larger units, like water and nitric acid. We now measure these atoms in nanometers. They are so small that an atom is to an apple what an apple is to the entire planet Earth. If you stacked millions of them, they would barely reach the thickness of this page. To weigh something this small, scientists use a relative scale. They use the carbon-12 isotope as the standard, defining one atomic mass unit as exactly 1/12 the mass of a single carbon atom. These aren't just theoretical concepts. Atoms are physical objects with fixed masses and measurable dimensions that dictate the properties of every substance we touch. Most atoms are unstable on their own. They are driven to connect with others based on a specific capacity for bonding. Think of an atom with high bonding capacity as an octopus with 8 tentacles, and a lower capacity atom as a human with 2 arms. To occupy every tentacle, it takes exactly 4 humans to satisfy the 8 limbs of the octopus. This fixed mathematical capacity is called valency. It determines which atoms can bond together and the exact number required to reach a stable state. This logic also applies to charged particles called ions, which use their electrical charge to form bonds. We derive formulas using the crisscross method. Aluminum has a valency of 3, oxygen has 2. Crossing these numbers to the opposite base reveals the neutral ratio, Al2O3. Similarly, calcium's valency of 2 and chlorine's 1 swap to form CaCl2. This rule allows us to determine the chemical formula for any compound by balancing the valencies of its constituent parts. Calculating molecular mass is the final step in quantifying a substance. It involves adding the masses of every atom present in a formula. For water, H2O, 2 hydrogen atoms at 1 unit each and 1 oxygen atom at 16 units total exactly 18 units. For nitric acid, HNO3, 1 hydrogen, 14 units for nitrogen, and 48 for 3 oxygens, total exactly 63. A single drop of water contains trillions of these identical units. Each one is a calculated arrangement of atoms, held together by the same constant mathematical laws measured over 2 centuries ago.